Yes.
is
Go
going.
Go ahead and hit it. Yeah. See if the numbers are
Okay,
scrolling.
then
There's the title.
go.
Okay, we're back, campers. As I noted before, it's hard to do demos in the class. We're going to try a couple more here today for the next section. Okay, so the topic we're moving into next, and I'm just introducing it here, are interparticle interactions. And particles can mean lots of different things. It can mean ions, it can mean atoms, usually not in our case, and it most definitely means molecules. So what does that mean? So interparticle means between particles. Intraparticle would be within the molecule. So you can think about intramural athletics within an institution and intercollegiate athletics, just to keep those two things in mind. So we're talking about interaction forces, attractions, repulsions between particles, not within. Okay, and some of this you already know from previous coursework. Now, the first thing I'm going to do is set up a demo that we're going to come back to later. So the demo is on these two molecules right here. This is a ring of 6 carbons called cyclohexane, okay, which we have a shorthand for this. You might recall some molecules we talked about where we had alternating double bonds. That's called a benzene ring. That is not this. That's a carcinogen. I'm not going to do a demo with benzene, okay? And this is a molecule we've probably talked about before, and we have various degrees of experience with. This is ethyl alcohol, okay? So we'll have that molecule here. So I'm not going to explain those two things. Those are just the electron dot structures which you're familiar with. And I have samples right here in these two containers. So cyclohexane and ethyl alcohol. And what I'm going to do is take a temperature probe. This is just a little demo here. I'll explain this later. And I'm going to measure how fast these two things evaporate. And remember what evaporation is. It's just molecules in the air smacking on the particles and going from liquid to gas. It's different than boiling, and evaporation is a cooling process. So when something evaporates, it gets cooler. That's why you sweat, for example, to keep your body cool. So that's a biology application. So here's what I'm going to do. I've got these two temperature probes. It's basically like a meat thermometer. And I'm going to get the temperature, start collecting temperature down here. I think it's collecting. Is it collecting? I don't know. Maybe it is. It's a very professional demo. Okay, so we're collecting data. I haven't done anything yet. So they're both starting off about room temperature. It's not that exciting. And it's collecting data for 500 seconds, which is a long time. So here's what I'm going to do. I'm going to take these two temperature probes and dip them in here, 1001, 1002, 1003. That's probably too much, but we'll find out. And then I'm going to let them evaporate. Oops, and I lost a rubber band. There's actually a good reason for why I lost the rubber band. And we're going to let those two things evaporate and collect some data over here, and we'll come back to that later just to see what that looks like. So I guess you could look at these and say, which one of these would evaporate faster than the other one? Maybe you have some ideas about that. And why would that be? Because that would have to do with how these two molecules, the forces with which they are sticking, if you will, to each other, the strength of their intermolecular forces. And that's something we'll talk about as the class goes on. Let's do some simpler things first, okay? So you already know about water. We've talked about water last semester. You've been talking about water probably since 7th grade. You know that water is polar. We've been through that. And that we also talked about in the last demo, if you dissolve salt in water, you get ion dipole interaction. So that's one of our forces. An ion, an ionic charge, positive or negative, interacting with the opposite charge of a polar bond or a polar molecule. So that's ion dipole. Fine. Well, water by itself, as you know, if you remember the Avogadro's number lab from last semester, we had the watch class, and we poured a bunch of water in there, and everybody got really nervous that you were going to spill, you were going to add too much water, it was going to go over the edge, which of course it will, but it fills up a lot more than you think it would, because you can see that skin kind of on the surface and the dome that Dr. McCann, who's filming this, is getting. And that's an important feature of water that not a lot of molecules have. And that particular kind of bonding is between water and itself. So it's water attaching to other kinds of water, and you know that that's called hydrogen bonding. But more generally, that's the dipole of one water interacting with the dipole of another water and another billions and millions, trillions, quintillions of times over in a watch glass. So that's dipole-dipole interaction, and the special case there is called hydrogen bonding, where hydrogen is bonded to a particularly electronegative atom, such as oxygen. So dipole-dipole interactions, ion-dipole interactions, and then something else we'll want to show you just for kicks. You all know that oil and water don't mix. You may have heard that phrase, like dissolves like. That's nothing new to you. Something like cooking oil, which I have over here, vegetable oil, is a variety of fat molecules, and it's a complex mixture. I'm not going to show you all of those. So vegetable oil doesn't have a lot of this, but this is a saturated fat molecule. It's called saturated because it has the maximum number of hydrogens that it can possibly contain in here. There are no double bonds. So it's carbon, 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 single, single, single bonds the whole way through to the end, and it's called a fatty acid. When you take organic chemistry, you have this acid part. So the idea here is this part of the molecule is different than this part of the molecule. Well, this part of the molecule is actually pretty polar. So it has a polar head, I think you've heard that before, and this other piece is relatively non-polar. So what I have here is a demo, just kind of a cheap one. Water in one graduated cylinder, vegetable oil in another, and you know that if you take food coloring and you put it in water, well, it disperses. Well, it should. It would be dumb if it didn't. So we could probably conclude that food coloring has some polar parts to it because it's interacting fairly well with the water. And if I let that sit there long enough, the second law of thermodynamics will take over, entropy, disorder, and it will spread throughout evenly. Now what happens if I put food coloring in with oil? I'm going to put in one drop, and I don't know if you can catch that on the video. It just kind of sits there at the top. It's not dispersing, it's just kind of hanging out. I'm going to try to add a little bit more. One interesting thing that the camera didn't catch, when I put that second drop in there, it isn't a second drop. It aggregated with the first drop. It went right to it and formed a larger drop. Oh, and there it goes. You getting that? It's kind of interesting. I mean, it's not that interesting, but you know, it makes the point. So the point here is you have a fairly non-polar solvent and a polar solute. Well, it's not really a solute, I guess, if it doesn't dissolve. And they don't want to interact with each other. The polar remains with the polar. The non-polar remains with the non-polar. And that's a very important thing, is that we can explain that based on molecular interactions. Very important, okay? So, and this one is polar interacting with polar, and they're perfectly fine on a molecular level interacting with each other because they have similar intermolecular forces. Both within the food coloring itself and the water, they're similar. But oil and the food coloring, no, and they will stay separate. And I think that's the last demo. And let's come over here. Oh, okay, that actually worked pretty well. I don't know if Dr. McCann can catch the graph there. It's not a huge difference, but here's what's going on. I'll make a graph here. So you've got, this is just temperature in degrees Celsius. I'm not going to make this too big of a deal, okay? And time in seconds. And what we see on this graph is they evaporate at different rates. They start out about the same temperature, and one of them dips and evaporates pretty quickly. Pretty steep slope. So that would cool your skin off faster if it wasn't like hazardous just to put this on your skin, okay? So we wouldn't do that, so we put a temperature probe. The other one, I'm making this exaggerated, does not evaporate as much. Well, I'm sorry, it evaporates as much at a lower rate, okay? Eventually, it'll all evaporate. So the idea here is if it evaporates quickly, that means that the intermolecular forces are very, very weak, and they turn into a gas very easily. And this one, the intermolecular forces must be a little bit stronger so that they're held together more and they don't go into the air as much. And it turns out that it's this polar part of ethanol. It looks an awful lot like water. That makes it a stronger intermolecular force. And and will evaporate much less slowly. Cyclohexane, by comparison, doesn't really have a polar part to it. Those are all fairly non-polar bonds and is a weak intermolecular force in its discraft. So in ethanol, we would have dipole-dipole interactions just like water. In cyclohexane, well, something's holding the cyclohexane together. It's a liquid. Something must be holding those together, but it's a pretty weak force. And that's the new one that we may not have discussed. And we'll discuss that in class.